Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving an interesting equation with complex numbers. I call this equation interesting for a couple reasons. First of all, I just want to tell you that I made a similar problem about a year ago, and I will share the links down below so you can go ahead and take a look at it. The only difference between this equation and that equation was on the right-hand side, we had z instead of z bar, which is the complex conjugate, right? I think the right way to say it is not conjugate, when you to conjugate something, but if it's a noun, that it's a conjugate. Anyways, I'll try to remember that. So we had z plus I equals zi, and that was number 8. Because I number problems that I believe were on now 400 something. I can't remember, but you'll see it in the title. I kind of keep track. So if you have any questions going back several months, I can't say several years because I think this channel has been around for a little over a year, I think, right? You probably know if you've been following me since the very beginning, and I know some people do. But anyways, I made a problem like this a while ago, and its solution wasn't too hard at all, and we found the solution. Can we find a solution to this problem? First of all, I want you to think about it. What difference does it make when you change the z to z bar? So you can go ahead and look at the other problem and compare. Maybe you'll get an idea from the solution method as well if you get stuck, okay? So anyways, we have this equation. How do we solve for z? If z appeared on both sides of the equation, we can kind of put it together just like we did in the other problem, or did we? And we could solve for z easily. But we have z and z bar, so that kind of tells me that I can probably talk about two different solution methods. What are those methods? Well, one of them is pretty obvious. I'm going to save it for the second method. But the first one is something a little bit more interesting, which is something we can use with complex conjugates. If you have z and z bar in the same equation, this is a method that can be used effectively and efficiently, hopefully. Okay, so let's see how that method works, and I'm going to call that first method. All right? So for my first method, I'm going to do the following. I'm going to conjugate both sides. So a couple things to know about conjugating. For example, if you conjugate the sum of two complex numbers, that also goes for difference because sum is a difference anyways, right? Or difference is a sum. Then this becomes the sum or difference of two conjugates. Great. And this property also works with the product. It also works with quotient, so on and so forth, right? Nice. It also works with the inverse, I think, like if you conjugated 1 over z, that would probably be 1 over z bar, right? Something like that. So I could go ahead and use that property here effectively, can't I? I can go ahead and actually conjugate both sides, and that should give me another equation, right? Hopefully. I keep saying hopefully because what is the outcome going to be? We don't know, right? Unless you tried. So if you conjugate this and that, first of all, on the left-hand side, we're going to use the sum property of conjugate. So it's going to be z bar plus I bar. And on the right-hand side, it's going to be z bar bar or double bar times I bar. Product is preserved, sum is preserved, and this is the equation we're getting. But wait a minute. What happens if you conjugate a complex number twice? It's kind of like taking the reciprocal. You get the same number. So z bar bar is z. It's like flipping a switch, right? Like a light switch, kind of binary. And I bar, because I is imaginary, its conjugate is going to be its opposite. So it's just going to be negative I. Make sense? And of course, the same thing applies here. This is just going to be z bar and then minus I. Great. So let's go ahead and write this in a simpler way. Z bar minus I equals negative zi. And the original problem gives us z plus I equals z bar I. Okay, cool. So hopefully I can use these two equations, and I'd like to, I'm lazy, so I'm not going to copy. I'm not going to write that again. I'm just going to copy and paste it because that feature is available for Notability. Thank you, Notability, for that property. So hopefully we can solve for z from here. So why don't we isolate z bar from the first equation, and that'll be I minus zi. And now you can hopefully substitute this right here and then solve for z. Let's try it. It's going to be fun. Trust me. Okay, z plus I on the left-hand side, and on the right-hand side, z bar will be replaced with I minus zi. By the way, you could also factor out an I here if you want, or just distribute the I, no big deal. It's the same idea. So now we're going to get z plus I equals, if you distribute I times I, it's just going to be a negative 1. And I squared is negative 1. And from here, we're going to get negative I squared, which is positive 1 plus z. Uh-oh. Surprise. The z's cancel out. Okay, you're like, oh, come on. We were about to solve for z, right? And we ended up getting I equals negative 1. Close enough, right? Well, the thing is, I does not equal negative 1. You hopefully know that. I squared is equal to negative 1. Does that mean I is negative 1? No, not at all. I is not even a real number, right? So I says I am not a real number. It's true, but if I say I am not a real number, I'm not a number. So anyways, you get the idea. I does not equal negative 1. So this is false. What does that mean? We did not get anything out of this. So this is kind of problematic, isn't it? Why don't we look at the second solution? Maybe the second method is going to give us something more concrete, right? Hopefully. Okay, let's find out. So we have z plus I equals z bar I, not zi, because that will be the old problem. Hopefully you will check it out and let me know what you think. Here, we're going to, what are we going to do? Oh, yes. Because we can't use the first method. It's over. We have to do something else. How about using the name of this channel? A plus bi. Yes, beautiful. We can replace z with a plus bi here. What about z bar? Well, z bar is just going to be the complex conjugate, which is a minus bi. Beautiful. Everything falls into place. Let's do it. A plus bi, isn't that exciting? Plus I equals a minus bi multiplied by I. Just appear to be excited, okay? Now, we're going to get the two imaginary parts together, so we can write it as b plus 1 as the imaginary part. And the right-hand side, we're going to distribute. This is going to give us negative I squared again, which is 1. So that'll give us b, nice. And then ai, like the artificial intelligence, right? Cool, cool. Can we solve this equation? Well, sort of, right? You can solve it, but we'll talk about it in a little bit. First of all, the real parts are supposed to equal each other. So a equals b from the first real parts. And from the imaginary parts are supposed to equal each other. That means b plus 1 equals a. But from the first equation, we get b equals a. So if you replace a with b or b with a, in the second equation, you get something like b plus 1 equals b, which is ridiculous, right? Just like the first method, b's cancel out and we get 1 equals 0. Wow, this is a great proof. You know, sometimes how they do those tricks on YouTube or sometimes shorts. Oh, we can prove that 1 equals 2 or 1 equals 0. Yes, this could be considered one of those. It's a trick, obviously. It's not true. This is false. What does that mean? This equation has no solutions. I mean, b can approach infinity and will have a limit, but no. Not even with complex numbers, and obviously a and b are supposed to be real, but this equation has no solutions, which means there is no z complex number that satisfies this equation. That's what makes this equation more interesting. So let's take a look at the result from Wolfram Alpha. Do you think Wolfram Alpha can solve this problem correctly? Let's find out. Ta-da-da-da. Yes, it can solve it by not solving it, by not finding a solution. You did the right thing. Good job, Wolfram Alpha. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.